Hi guys, let us discuss Bellman-Ford algorithm. The Bellman-Ford algorithm finds the shortest path from a single source vertex to all other vertices in a graph. For example, in this given graph, we will take the source vertex as A, and this Bellman-Ford algorithm is used to find the shortest path from this source vertex A to all other vertices in this particular graph. And also the unique feature of Bellman-Ford algorithm is the weights given for the edges may be negative also. So that is a unique feature of Bellman-Ford algorithm. Step is to create a initial table like this. Source vertex is A and the other vertices are B, C, D, E, F, and initially you keep all the distances as infinity as shown in this table. So we create an initial table with the distance from source vertex to all other vertices as infinity. With that, we move to the next step. So the next step is the first iteration. So from this source vertex, you identify the nodes which can be reached with a single edge. So that means we can reach from A to B with the distance 6, from A to C with the distance 4, and from A to D with the distance 5, and all other distances are as it is with the infinity. That means for A to E and for A to F the distance is kept as infinity. So next we move to the second iteration. The second iteration, what we should do, from this source vertex A, and we should find the nodes which can be reached with the two edges, and if the distance is smaller than the previous table, then only we should update. That we should remember. So for example, if we take from A to B, in the previous table we are given it as 6, but now I am trying to find the path from A to B with the two edges. So two edges means I can go from A to C and C to B. So 4 minus 2, 2. That is what given here, 2. And for C, is there any way we can find a path with lesser than the previous weight with the two edges? So previously A to C was 4 in the previous table, but now two edges means I can go from A to D and D to C. 5 minus 2, 3. So that is what given here, A to C is 3. Like that for A to D, even after having two edges, the distance does not change. So A to D is only 5. For A to E with two edges, so what is the way to reach from A to E? In the previous table, A to E was infinity. Now, as I am trying with two edges, so what is the way? 6 minus 1, that is A to B, B to E. So 6 minus 1, 5. I can reach A to E through B with the total weight of 6 minus 1, 5. For F, now I am trying to find a path with two edges. Previous table, that is in previous iteration, A to F was infinity. But now I am trying to find a path with two edges. So A to D, 5, and D to F minus 1. So 5 minus 1, 4. So that is the A to F was updated as 4. In the third iteration, we should try to find a path from source vertex A to all other vertices with the three edges. So for example, if we take A to B, the previous entry in the second iteration was 2, that is distance was 2 in the second iteration. Now for A to B with the three edges, you can travel like this: A to D 5, D to C 5 minus 2, 3, C to B 3 minus 2, 1. So I will update the entry as A to B as 1. For A to C, the previous entry in the second iteration was 3, but now even after having three edges, we are not able to identify a path with a lesser distance, so we will keep it as it is. For A to B also the similar case, we are not updating because we are not able to get a distance with a lesser distance. For A to E, now with the three edges, so you see that in previous table the entry was 5, but now for with the three edges A to C 4, C to B 4 minus 2 2, then B to E 2 minus 1 1. So now A to E distance is 1. So this 1 is lesser than the entry in the second iteration. So I will update A to E as 1. But for A to F, the previous entry in the second iteration was 4. In third iteration also, I will keep it as 4 because even after having 3 edges, we are not able to identify a path with a lesser distance. So that is the important point in this algorithm. That means in each iteration, if you are able to identify the path with the lesser distance compared to the previous iteration, then only we should update. Otherwise, we need not update. So we are moving to the fourth iteration. So in fourth iteration, I will try to find a path from source vertex A to all other vertices with the 4 edges. Here for A to B, the previous entry was 1 in the third iteration. In fourth iteration also it is 1 because I am not able to identify a path with 4 edges from A to B with a lesser distance compared to the previous iteration. So that is the case for C and also for D. The same entry was kept as it is because we are not able to identify a path with a lesser distance. But in case of E, A to E, we can identify a path with 4 edges like this: A to D 5, D to C 5 minus 2 3, C to B 3 minus 2 1, and B to E 1 minus 1 0. So I will update A to E as 0 because this is lesser than the entry in the previous iteration. For A to F, there is no change because we are not able to identify a path with the 4 edges with lesser distance compared to the previous iteration. So now we are moving to the next iteration, that is fifth iteration. We are trying to find a path from source vertex A to all other vertices with the 5 edges. So here for A to B, we keep the same distance as it was in the previous entry because we are not able to identify a path with the 5 edges with the lesser distance compared to the previous table. The similar case was for C, D and E. But only for F, I am able to find a path with 5 edges like this: A to D 5, and 5 minus D to C 5 minus 2 3, and C to B 3 minus 2 1, and B to E 1 minus 1 0, and E to F 3. So the distance 3 is lesser than the entry in the previous iteration. That is, in the previous iteration it was 4, so now it is 3. So I will update A to F as 3. So this is the final answer. Why I am concluding here? Because there are 6 vertices are there, so that means we should go for number of vertices minus 1 iteration. So 6 minus 1, 5 iterations we have to go. So we have completed 5 iterations. So the final answer is A to B distance is 1, A to C distance is 3, A to D distance is 5, A to E the shortest path is 0, and A to F the distance is 3. So this is the final answer after 5 iteration. So we should try number of vertices minus 1, that is 6 vertices are there. So 6 minus 1, 5 iterations. With this we complete this process.